Welcome to ISCFDC EZOpt tutorial. In this tutorial, we will learn how to use the loop node. Let's begin by adding an input node, a calculator node, a loop node, and connect them. We'll rename the calculator to sum and give it the value of 0. This is the loop node. Like the if node, it has two branches. The right branch is the pass or true branch, and the left branch is the fail or false branch. Now we'll see how to set up a loop. Double-click on the loop node to open it. This is the loop nodes window. It is very similar to the if nodes window, but with the addition of an extra option, iteration limit. There are two kinds of loops: a while loop, a loop that keeps repeating as long as the loop condition is met, and a for loop, a loop that repeats a prescribed number of times. We'll begin with a for loop. We'll give the loop condition, which is basically an if statement, an always true statement, if 1 is greater than 0. To do that, we will do the next three steps. Change the constraint to greater than, change the value to 0, and write 1 in the expression. Now we can decide how many times the loop will be repeated. To do that, we will change the iteration limit field from not limited to any number. Let's choose 5 and click OK. EZOpt loops are basically while loops, with a built-in flag, which is the iteration limit. When iteration limit is not limited, the loop only has one condition, the condition set by the user. When iteration limit is a number, a condition for the iteration limit is being added to the loop's condition, with a logical AND between them. Now we'll add a modify node, connect it to the past branch of the loop, and open it. In the modified node's expression, we will write sum plus input 1, and set the overwrite node to be the calculator we named sum. With this, we will expect sum to have the value of 5 times the value of input. Now, we'll add an exit node and connect it to both branches of the loop. The loop in EZOpt works in a way that the node connected to both branches is considered to be the line in the code that comes after the loop is closed. The exit node will not be executed by the right branch, since it also needs to get a signal from the left branch. Now, we'll set up a DOE with 11 designs, click OK, and run the workflow. Let's take a look at the results. We can see that for each input, the value of sum is 5 times the corresponding input, as expected. Now, we'll set up a while loop and also show how to use the calculator functions like sum and average with the need for a node before the loop. Open a new workflow and add an input, a calculator, and a loop node. Change the calculator's name to counter and set it to 0. Connect the nodes and double-click on the loop node. In the loop window, do the following. Change the constraint to less than, change the value to 5, change the iteration limit to 50, never use unlimited unless you are certain that you will not enter a never-ending loop, and write counter in the expression and click OK. Add a modify node and a calculator node and connect them to the pass branch. The order of the connection is insignificant since they do not affect each other. In the modify node, choose counter as the override node and write counter plus 1 in the expression. Change the calculator's name to sum, the evaluation option to sum, and write input in the expression. Add an exit node and connect it to both branches of the loop. Set up a DOE with 11 designs, click OK, and run the workflow. Let's take a look at the results. We can see that we have the same results as we did with the for loop, but this time we also have the counter node's value added to the table. Let's show another example. In this example, we have a workflow that checks if an input number is prime or not. According to the Wikipedia definition, a prime number, or prime, is a natural number greater than 1 that is not a product of two smaller natural numbers, or in simpler terms, can only be divided by 1 and himself without residual. The algorithm for this workflow is as follows. First, we get an integer number between 2 and 1000. Next, we set two flag variables, one for the loop, called flag, and one for the result. Is the number prime or not? Is prime. We set the initial denominator, the variable input is divided by, to 2, and calculate the square root of the input. Checking if a number is prime or not is done by dividing it by 2 and all the odd numbers up to and including its square root rounded down. We check if the result of the square root minus the denominator is equal or greater than 0. If negative, which is the edge case that covers 2 and 3 as inputs, the number is prime and we finish the workflow. If the result is 0 or positive, we continue to the loop. This is our loop. This is a while loop that runs as long as flag's value is 1. We set the iteration number of the loop to 20, which is more than enough iterations for the loop to check if all the inputs in the 2 to 1000 range are prime or not. Setting the iteration limit to a number lower than the number of times a loop is supposed to be executed will result in the loop stopping when the iteration limit is reached instead of when the loop condition is no longer met, and the rest of the workflow being executed until finish. The loop ends when flag's value is 0, and when it ends, so does the workflow. Inside the loop, we calculate the residual of the division of input by the denominator. This value can only be equal or greater than 0, since a number, x, is always equal or greater than x rounded down. We check if the residual is equal or less than 0. If true, that means the residual is 0, then the number is not prime. Using modify nodes, we change the is prime and flag to 0 and close the loop. If the residual is greater than 0, we check if the denominator is greater than 2. If not, then denominator is equal to 2. Then we use a modify node to change the denominator to 3. If true, we advance the denominator by 2. As we said before, since denominator equals to 2 covers all the even denominators, all we are left with is checking the odd denominators. Now, we check if the result of the square root of the input minus the denominator is still less than 0. If true, we change flag to 0 and close the loop. If not, we close the loop without changing anything. We'll set up a DOE using Latin Hypercube and run the workflow. Let's take a look at the results. We'll arrange the results table by ascending order of input. We can see that for inputs that are equal to 2 and 3, we have both flag and isPrime equal to 1, meaning we didn't enter the loop. For greater inputs, we have flag 0 and isPrime's value is 0 for non-prime numbers and 1 for prime numbers. We can filter out the designs that aren't prime by clicking on the gear icon next to range filtering. Clicking on the plus sign under node values main, select isPrime as our filtering parameter, change the 0 in the minimum field to 1 and click OK. Now we are left with a list of all the designs that are prime, 11, 13, 17, and so on and so on. This is it for this tutorial. Thank you for watching.